All right, everybody, welcome back. Sorry, we're off to a little bit of a late start today. So at this point, we are done talking about sorting, and we're going to move on to a topic that is near and dear to my heart, something that I really enjoy teaching about for the next few weeks. We're going to do a mix of things. We're going to do a little of talking about the internet, and there's a couple of Java concepts and ideas that we're also going to sneak in here towards the end of the semester. So we'll look at exceptions and errors, and then also a generic programming in Java, which allows us to build, general purpose data structures that can handle lots of different objects, but also do that safely in a way that utilizes Java's compiler to provide compile time safety. But today is more of a fun class where we're going to look at the internet. I feel sort of very drawn to this topic and excited to teach about it every semester. Because on some level, this is kind of like the flowering of computer science. If you think of all the things that computer science has contributed to the world, the internet is probably one of the most important. In fact, I would probably say it is the most important. Particularly now, we're kind of understanding, starting to realize just how foundational the internet and the World Wide Web as well, which we'll talk a little about over the next few classes, are to our daily lives, particularly in this period of time when we're all quarantined. This is how many of us are having things like groceries and other, supplies delivered to our house. This is what's allowing us to communicate with each other. It's what enables this very class that you guys are participating in today, as well as all the other activities that go on with this class. And again, this is a topic that I think, is worth coming out of an introductory computer science course with a little bit of understanding and knowledge about. It's also just super fun to talk about because there's so many different moving pieces. It's this incredible technology success story. What it has wrought, right? The type of things that have come out of it aren't all positive, right? I mean, certainly not. We look at how Facebook has been manipulated to influence our elections. We look at the types of misinformation that are being spread across the internet on certain social media platforms and in other ways. So in no way am I claiming that the internet or the web is fundamentally a good thing, but I will claim that fundamentally it's a great piece of technology. The computer science design decisions and technology choices that went into the system are fantastic, and they have stood the test of time for decades and decades and decades. If anything, if we think about now all the additional load that's being placed on the system, it's actually holding up pretty well, right? And this is by design. So I'm gonna, today we're gonna start talking a little bit about sort of like, what is the internet, right? What do we mean when we talk about it? How does it work, right? What are some of the infrastructural building blocks that comprise the actual physical infrastructure that makes up the internet? Because that's always a fun thing to look at, I think. I like physical infrastructure. But we'll also talk about a little bit the protocols that are used to move data and content across the web, and then across the internet, and then a little bit about the World Wide Web itself, and how web documents are structured and how they work. All right, so the goal here is really to get kind of backtrack a little bit and get you to the point where you can understand a little bit about some of the communication that you have finished implementing between your app and our backend server, right? Both in terms of the usage of web APIs, WebSockets, and things like this. But before we can talk about web APIs, we have to talk about the web. Before we can talk about the web, we have to talk about the internet. That turns out to be not such a bad thing because the internet is incredibly fun to talk about. So again, this is one of my favorite topics. There's this whole website that you can go to where I recorded a bunch of short videos about this topic that are still on the internet, on internetclass.org and on YouTube as well, on our YouTube channel. So if you're interested in some of these topics and you have some time on your hands, they're out there. Gives me a chance to get into more details about specific features and aspects of the internet that we're definitely not going to get a chance to cover here. I taught an entire course on this once at another institution. All right, so let's start with this basic question, which is, what is the internet? And there are multiple different ways to approach this question, right? Because the internet actually means a lot of different things. But where we're going to start today, the first place, I think, is that the internet as stuff, the internet as an actual piece of physical infrastructure. because this is, at the end of the day, what underpins all of the higher level communications that go on over the internet, right? I mean, you can't stream something across the internet without the internet infrastructure that we've built to support this incredible technology. So what I'm showing you right here is a map, obviously a map of the United States, but what's overlaid on top of it are what are known as the internet backbone links, the core internet backbone links. So these are extremely high speed, high capacity links that move data large distances across the country. So just off the top, let me address a couple of common misconceptions. First of all, on the internet, data is rarely moved over a wireless connection. You guys experience wireless at the edge of the internet. This is at the very end. So in many cases, the last transmission over the internet is potentially a wireless transmission, either to a laptop or to a phone or something like that. But the majority of data moved on the internet is moved over wires, cables. It's not moved wirelessly. Wireless turns out to be too slow and too limited capacity. So essentially, even if you're using your mobile phone, the data is transmitted to your phone over wireless connection, but the data from the tower that the phone connects to, and we'll look at some examples of this in a few minutes when we continue to look at various pieces of infrastructure that comprise the internet, the data from the tower that your phone connects to, that data hits a wire, and then it's pretty much on a wire all the way to where it's going. And that's because these wired connections just could provide so much more bandwidth and speed than the wireless connections that we use at the edge. So what's shown here are, again, these internet backbone links. These are cables, buried cables. And one of the things that's fascinating about this map, to me, right, when you think about the history of infrastructure, because essentially what we're talking about is infrastructure, right? For about half an hour of today's class, this is now a class on sort of infrastructure, which is important because this is sort of how the internet works at a base level. But what's fascinating about this map is that, we'll get down and we'll look at some other maps in a minute, but what's fascinating about this map is that some of you may recognize certain features of this map, and that's because in many places, the internet backbone links run along the same routes as the interstate highway system, right? Now, think about it. That makes a little bit of sense, right? These are, this is infrastructure. From time to time, stuff breaks and somebody's got to go out and maintain it. And also when we were actually, laying out these cables in the first place, it made sense to do it along on routes where it was easy to get equipment to, right? So, this is why in many cases this runs along the old interstate routes. What's fascinating about that is a lot of the old interstate routes were laid down along old train lines. So we're still seeing the legacy of decisions about how to connect the country that were made hundreds and hundreds of years ago. When those first people built the first set of transcontinental railways, they made choices about which routes to run, and we've actually been echoing those decisions decade after decade, century after century, even after we moved from, the railway system to the superhighways to, as Al Gore put it, the information superhighway, right? We're continuing to use these same routes. So again, if you think about, like, let's say you're on a Facebook server, and let's say that Facebook server is actually located in California, which is unlikely, but let's say it actually is. So you think about, like, if you're somewhere in central Illinois, how is your connection with that server going to be established? Well, if you're in central Illinois, you might end up on one of these high capacity links here, and then you're going to hit a few hops going across the country until you get to the Bay Area. But these high capacity internet backbone links are the real workhorse for moving data across the internet. The goal of any internet connection, of any data transfer that takes place across this network, is to get to one of these high-speed backbone links as quickly as possible. Because once you get to one, it's very, very quick to get to where you're going. Again, the analogy with the highway system is not actually that inappropriate. So you think about how you take a long trip in this country. Let's say you want to, go to Seattle or something like that, right? Well, I start from my driveway, I'm on a small road, I make a couple of turns, but my goal is to get to an interstate, right? To get to a highway that's a high-speed link. And as soon as I'm on that highway for pretty much all of the trip, right? As much of the trip as possible, because the highway has higher speeds, I don't have to stop and things like that. Once I get to my destination, I have a couple of small, little detours. Maybe I'm going to see my sister or whatever. I have a couple small little bits of the trip that I have to finish once I get there. But the goal is to put as much of that travel time onto these high-speed, high-capacity roads that don't have lights and things like that are designed for to move people quickly from over long distances. All right, so you might wonder, well, how does internet? You said we don't use wireless that much. Well, how do I get data across continents? Here, again, we rely on physical infrastructure, and again, that physical infrastructure is echoing routes that were laid down over centuries. So this is a map. You can find this online. Actually, it's probably a couple years old, of the different routes that are being served by undersea cables. So again, if you go to a website that's hosted where the server that runs the website is actually located in Australia, you're not going to be on a wireless connection. Way too slow. Instead, what's going to happen is your data is probably going to be transmitted over one of several undersea cables. And these are cables that have been strung over, by ships over hundreds and hundreds of miles. You can imagine some of the logistical and technical challenges involved in maintaining this type of system. I mean, literally, there are cables that are lying on the bottom of the ocean that are ferrying internet communications from one continent to another. What happens if that cable breaks? What happens if there's a problem or whatever, right? So the levels of reliability that are required for these systems are actually pretty high. And the fact that these are working as well as they do is really an impressive accomplishment, right, to be able to do this. Now, again, you can see sort of on this map different routes that have been strung. So, for example, there's quite a bit of connectivity from the west coast of the United States over to Asia, and quite a bit of connectivity between the east coast of the United States over to Western Europe, and then also south to northern South America, and then also over to Africa. And so, again, depending on where where site you're trying to connect to, your data might be moved across one of these undersea cables as well, right? So one thing I want to point out that's really interesting about this whole system, right, is that we've built a worldwide communications network where, for the first time, maybe in human history, we really do have this international system that is something that everyone is bought into and we all cooperate to maintain. That's not true of a road network, right? Road networks have different rules in different countries. You have to switch sides of the road, right? Whatever. We have some common rules so that, most of the time when people can drive in one country, they can figure out how to drive in another country. But there's still these weird local conventions that end up being followed. With the internet, we're actually moving data all over the world, and this enables data transfer between countries that might be at war with each other, right? Countries that don't like each other very much, right? You can get on the internet today and go to websites that are hosted by countries or run in countries that the United States considers itself to be an enemy of, right? And yet, we're all cooperating together to build this, worldwide communications infrastructure. And this is one of the reasons I've always, really loved talking about the internet is I think that on some level, this network, this system is one of the ultimate embodiments of our need to communicate with each other. Humans are creatures that are social, but we also need to communicate, right? Right now, we're all stuck in our houses, and so that need to be around each other is being impinged on. But the internet is still happily facilitating our need to communicate with each other. One of my favorite stories about this was, being at a bar in Singapore once on free Wi-Fi and video chatting with my wife, who was located back in Buffalo at the time, halfway around the world. And we as humans have built a system that facilitates that sort of thing. That's incredible, right? I mean, if you think about the things, we still don't have flying cars. We still don't have, a vaccine for the coronavirus yet. But we've been able to build this worldwide system that enables a type of communication that people even 100 years ago would have thought was completely science fiction, right? And that's a pretty incredible achievement. At the base of this, supporting this whole system is a type of connection, right? So again, talking about physical stuff, these are cables, right? Cables that, come up on one end of the Atlantic and submerge under the water and then emerge over in France or whatever, right? And there's literally like you could tug one end and the other end would move. These are cables, right? What's inside these things? So the other, and this I think this surprises some people, right? Because it's also very different than the type of cable that you normally associate with the internet. But one of the other big enabling technologies for this entire system is something called fiber optic cable, which you might have heard of, but it's glass. So the conduit for all of this high-speed data transfer around the world is not these copper cables that you might be familiar with that you use when you plug a computer into an Ethernet jack at your house or at your dorm or whatever. The big high-speed data connections are done on fiber optic cable. And the glass inside this cable is also incredibly special. It took years and years and years of extremely interesting engineering to create glass that was pure enough to be able to transmit data over long distances without it, the signal weakening to the point where you couldn't actually, the data would get lost, right? And so it's interesting. I used to live in upstate New York. There's a pretty famous glass company in New York called Corning. You go to their headquarters, and this is a company that used to make like glasses that you would drink pop out of or whatever, right? And you go to their headquarters and it's kind of a weird experience because it's like all really nice and like super fancy, and you're thinking like, what's going on here? Where's all the money coming from that's supporting all this? Where it's coming from is from fiber optic cable, right? I don't think Corning makes money off of their dishware anymore. Instead, they are one of the world's leading suppliers of high quality glass that can be used to create files at high enough qualities to be able to support this type of data transfer. So to summarize, fiber optic cable, I think actually they were one of the first companies that was able to make, the first thing that the internet is when we talk about what the internet is its infrastructure, it's stuff. And it's an enormous amount of physical infrastructure. I mean, I don't know, I'm sure someone has done a calculation in terms of what the overall worldwide investment in internet infrastructure is. I suspect it's at least in the trillions of dollars, right? In terms of the cables and the towers and the ships and the crews that had to pull the transatlantic cables, right? And all the buried cables, right? It's a huge amount of infrastructure that we've invested in this problem of connecting people together. Again, to summarize, most of it's wired. This is wired infrastructure. Wireless is used at the very edges. We'll talk about wireless in a minute, but most of the core internet infrastructure that moves data quickly from place to place consists of wired connections, not wireless. And most of that wired connection is glass. It's not copper. You see copper at the edge, right? If you cut open one of these cables that you can buy over at Home Depot and look inside, you'll see a copper cable, very similar to an electrical cable. But that's only used at the very edge of the network. In fact, copper cables can typically only be used to transmit a signal about 100 meters before the signal inside that cable has weakened to the point where it needs to be amplified again, right? So, you can't run a copper cable for a mile. The signal inside that will never make it from one end to another. And so if you look, and actually at the University of Buffalo, I did this. I found, you can always find these people on campus. There's I'm sure this is true in Illinois too. There's maybe 3 or 4 people on staff here who know everything about how the campus network works. They know where they have keys to every single networking closet. They know where all the basement connections are made between buildings. And so at Buffalo, I found one of these people, and he was, helpful enough and kind enough to actually walk me through this. So we started in my office. We looked at what was behind the wall there. That's a copper cable. What he pointed out is that in the building, and this is probably true in Illinois as well, within 100 meters of that first connection, typically what happens is that copper cable that you would plug into in a wall jack in your office, that copper cable runs up through the ceiling and down the hall and stuff like that, and ends up in a networking closet, one of these, innocuous, unmarked closets that you find in buildings all over campus, where it plugs into a device that converts it to a signal that's transmitted over a fiber optic cable. So you see these, you go into this closet and there's this big device, and on one side of it you've got all of these copper cables plugged in, and the other side you might have like 1 or 2 of these incredibly slender, thin fiber optic cables. And all of the data that's being transmitted by this big, mass of copper is coming out over those two tiny little pieces of fiber optic cable, just because they're so high capacity, right? You don't need as much of it. So, the goal when designing some of these campus networks or home networks, residential networks, is to get to fiber as fast as possible. When you look at things like Fios from Verizon and some of these other technologies, it's the same game, right? Essentially what these companies are doing that are providing fiber, whether it's Google Fiber, which they were doing some experiments with at various places in the Midwest, or Fios, which I think is sort of like, seems to happen and then not happen. There's a local company in Champaign that's been laying fiber. What they do is they try to bring the fiber a lot closer to your house. So then you can make a single connection over a copper cable to fiber that might be, on the utility pole behind your house. And this is why, again, if you look at the rollout of this in Champaign, in the Champaign-Urbana area, there's some, it's literally kind of street by street. There's some blocks that have it, and there's some blocks that don't. And the reason is, some of the blocks, the company has decided there's enough interest in that area that they're actually going to have to pay to pull fiber optic cable all the way to that place, and then they can connect a few customers. If you don't have enough interest, they won't do it, right? So this is a very localized process. And again, if you think about all the different ways in which the internet could potentially not exist today, right? And we're going to talk about a couple. The core enabling technologies that enable the internet as we know it today, one of them is by far fiber optic cable. I mean, we just could not, the internet would cost, 1,000 times more than we've already spent on it, which is still a lot, if we had to run it on the back of copper cable, and it probably just wouldn't work at all. So fiber optic cable, you might not have known this, but that high quality glass is one of the things that has created modern life. Right? Particularly the kind of modern video chat-based existence that we're all surviving with right now. So again, I have a series of videos online if you kind of want to walk through this. This was a pretty neat experience for me. So essentially, we started in my office. We looked at what was behind the wall. We followed that to the networking closet that was down the hall. And then, we followed that down through the basement out to a connection that ran over to another building on campus. And then we followed that out. And eventually, this is super cool, right? Again, I'm sort of a geek. I'm into this stuff. I was in a room. It's in this, it's like they blindfolded me to take me in there, right? They didn't want me to know where this was. But I was in this room in the basement of a building on campus, and I was looking at, where all of the data from the entire University of Buffalo campus entered and exited, right? So there was one spot where, all of the campus's connections came into one place, they all ran into one place, and then left to go meet the rest of the internet. And it turns out, right, when I was sitting there looking at this, it's this tiny little piece of cable, It's not, you would expect it's like this big pipe because it's got all this data in there, but no. Fiber optic cable is so incredible, it can carry so much data that essentially it was just this one little thin strand of fiber optic cable that was then running to downtown Buffalo where it would meet up with other networks and things like that. But that was pretty cool, right? A pretty incredible illustration of just how high capacity these fiber optic wires are. All right, so now let's talk about wireless, right? So we've been talking about the wired backbone of the internet, but wireless is obviously such an incredible and important part of your modern experience of the internet. This has changed, in the past 30 years, right? This has changed the experience of the internet, I think, more for the users than any other thing that's been happening, right? I remember being in college, and it was like you got there and you had your desktop and you plugged it into and a few people had laptops, but the wireless was only in a few places, right? And now it's like, we expect to find wireless everywhere, and increasingly we do. So how does that work? Okay, so wireless is provided, again, primarily at the edge of the network through a couple of core technologies. One of them is called Wi-Fi. Wi-Fi is, if we were in Lincoln Hall together right now, which we're not, obviously, but, I would point out, and these are pieces of infrastructure that are very easy to miss, all the different Wi-Fi routers located around Lincoln Hall, and there's 8 of them, right? They look like this on campus. This is a company called Aruba that makes Wi-Fi hardware and is one of the vendors that the university has used to provide Wi-Fi access across campus. Critically, what you can't see in this picture is that running in and out of this is a wire, right? So again, even if your first connection to the internet is over a Wi-Fi connection to a wireless router, the second connection is across a cable, right? And so again, the core internet infrastructure is all wired. The last connection that you make frequently today with your mobile phone or your laptop or whatever is wireless. Given that many of you are at home, you probably are more aware of this than you might be at school because, you know, the family Wi-Fi router is like in a closet somewhere, like mine's over there in the closet in the back of the room, right? And maybe from time to time it goes down and you got to go reboot it or whatever, right? But this is an incredibly important part of the modern internet, is this last hop wireless. We also, so Wi-Fi is great for short range connections, and it's frequently set up for personal use. So if you go to New York City or to Chicago and get out your phone, it's a fun thing to do. You might be able to see like 50 or 100 different Wi-Fi connections at a particularly busy place because, you know, you've got an apartment building and every single apartment in that building has a separate Wi-Fi router. We've also set up larger scale wireless or more long distance wireless, and this is the type of connection that you get when you go outside of your house. So you take your phone, you know, at home your phone is probably connected to a Wi-Fi network, but when you leave the house it switches and now it's connected to a mobile data network, right? And these are provided by these towers. And again, this is more infrastructure. And when we talk about 5G networks, for example, which is the next generation of mobile data networks, we're actually going to have to deploy even more infrastructure. So you might wonder a little bit why you pay Verizon so much every month, and part of that is because they are maintaining and improving and upgrading an enormous amount of physical infrastructure. It's not only the only reason, they're also ripping you off a little bit, but they do actually have a fair amount of actual real network out there in the world that they have to take care of. All right, so this is the most common manifestation of sort of mobile broadband or mobile data networks, right? Some of you may have noticed these before. If you haven't, I hope that you'll notice them now. When you drive around, particularly when you're on an interstate, when you're in a city, look for these. You will see them all over the place. This is a cell tower. One of the things that's very distinctive about these towers is that they have this equilateral, they frequently, particularly when they're out in open space. Now, when you're in a city, you might see these antennas, which I can't highlight very well here, but these white, the white vertical things, those are the actual antennas that are sending and receiving data. And you'll see that they're mounted on the tower in this way so that this is an equilateral triangle. And you know what's interesting here is that a little bit lower on this tower you see another equilateral triangle that's tilted slightly differently, right? The reason why they're triangles is because it turns out when you tessellate space, the most efficient way to cover a large area in a way that provides equal coverage, because essentially the goal is whenever someone is anywhere in the country, for example, Verizon wants them to be within range of one of their towers. The most efficient way to do that is to break space into hexagons. And it turns out at the intersection of every hexagon, you have three different, I don't think I can do it with my fingers, right? But you kind of have three different parts of different hexagons coming together. It's at those vertices that you put the towers. So one of these sides is facing into one cell, this is facing into a second cell, and this is facing into a third cell. And I suspect, although I don't know, that this particular tower, and this is common, is being used by two different service providers. And that's why you see that the two equilateral triangles are twisted slightly differently, right? One provider has set up their cells in one way, and another provider has set up their cells in a slightly different way. And as a result, this tower that they're both sharing is the two triangles are not aligned, right? This could also be for two different generations of a network used by the same company. I don't know. But again, you'll see a lot of this once you start looking for it, right? Because in order to provide, again, if you think about it, every time you use this phone out when you're like out and about and you're actually accessing the internet, your phone is talking to one of these. It's the same technology we see at home, right? At home, you know where the Wi-Fi router is. It's in the closet, right? Or it's, behind the sofa or behind the credenza or whatever. When you go out and you're using a mobile data network, you don't know where the routers are, but they're still there. And it's actually kind of amazing that your phone can talk effectively and actually, get a reasonable connection to a tower that might be a quarter mile or a half mile away, right? Certainly a tower that you may have never even noticed before, right? But it's by deploying these towers and this infrastructure that we've created the ability for you to use the internet pretty much everywhere you go. Not everywhere. There's certain parts of the country where not very many people live, and so it may not be super, cost effective to provide great internet access there. But particularly in dense urban areas, there's pretty good coverage today, right? All right. So again, over the past couple years, I shouldn't say couple years, over the past couple decades, we've also augmented the existing wireless backbone of the internet with an enormous amount of the existing wired backbone of the internet with an enormous amount of wireless infrastructure. And this is what allows us to essentially provide ubiquitous continuous internet access. So today, you can basically spend your whole 24 hours a day, with access to the internet, right? Connected all the time. There are good things about this, there are bad things about this, but it's undeniably impressive just from a technological perspective. So again, just to summarize, the short-range wireless connections used at home are dominated by a technology called Wi-Fi. That's what's used on campus, at home, in a coffee shop, on a plane. It's a variant of that. And then when you go out and use in a mobile data network, you're using something called medium-range wireless, and that's used to provide connectivity to devices when they're outside of the range of like a Wi-Fi. So, the internet, despite the fact that the internet is now this sort of global phenomena, the internet is also something that we're not done with, right? This is not a technology that we have finished deploying. This is a map showing internet usage over time across the entire world. So essentially like, the map is color coded. So, it's, I think red is higher levels of usage, blue is lower levels of usage. And so you can see as the days pass, usage goes up in the day, goes down at night to some degree, but particularly in places that have good internet access, it never really stops. There's always somebody using the internet. However, if you look at this map, you can also see one of the biggest challenges that we have ahead of us in terms of finishing the deployment of the internet, which is that on some level, some of the coloring in this map represents population density, right? So if you look at, India, you look at China, you look at Europe, right? You can see big population centers, right? You look at Eastern South America, right? But the map also reflects just, internet access and the penetration of infrastructure to different parts of the country, right? So the entire United States is lit up, despite the fact that the population density of some places in the United States is incredibly low. Whereas if you look at Africa, it's incredibly dark, despite the fact that there's an enormous number of people that live there. So today, and the numbers change a little bit every year, but today, I think the number is about half, maybe 60% of people on Earth have regular access to the internet. Now, again, by regular access to the internet, we don't mean they have a smartphone that's always online, although frequently, particularly in third world countries, the way that people are connected to the internet is through a phone. But by regular access, we mean something like maybe once a week, they have a period of time where they can access the internet, check email, whatever. That might be in an internet cafe. It might be through a device that, they can't keep charged very often. It might be through a device that costs money that they can't afford to use all that often. But, so again, we're a long, long, long way from everybody having the type of internet access that people in the United States enjoy. Always on, always in your pocket, ubiquitous access to connectivity. Most people on Earth don't have that, but we're getting there. And there's been some exciting new developments over the past couple decades in terms of new ideas of how to make the internet more accessible to more people. Because partly, if you think about some of the exciting benefits and opportunities that the internet opens up, the percentage of the world that doesn't have internet access, when we bring them online, things are going to get very, very interesting. Because in many cases, these are people for who internet access has the potential to transform their life. Not just as a convenience, but as something that's really going to completely remake the way that they live. All right, so All of this investment in infrastructure, wired infrastructure, wireless infrastructure, means now that by connecting to a computer, your computer to the internet, you have the possibility of interacting with something like about 4 billion, and it's probably more than that now, other computers. Like, that's what we have built, right? You don't typically connect to very many of those 4 billion other computers, but when when your device associates with the Wi-Fi, when you turn on your mobile data network, you are now in a position to exchange data with billions and billions and billions of other devices all over the world. A lot of times, again, to summarize, your first connection is wireless. Most of that connection past that point is on a wire. So if you think about it, you could actually, anytime you connect with any device on the internet, you can find the path that your data is taking. Your data is being transmitted over a wire. So you could literally walk that route. You might have to do some swimming if you're going overseas, but you could follow the cable all the way from one device to the other computer. So when you're on Facebook, you're connected to some computer in one of Facebook's data centers. And you could follow the connection, you could find that data center, they're not gonna let you in, but you could locate that data center and you could be like, okay, well, literally the computer I'm talking to right now is in that building with lots of other computers. Okay, so far what we've done is we've created the substrate, right? We've connected devices. There is a wire that connects the two devices that can carry a signal. That's one way to think about it. But now we have a much more interesting question to solve, because we've done the electrical engineering kind of to get ourselves to this point. But now what do we do? So how do we set up ways that these different devices can actually communicate in meaningful ways, right? So the internet is not just physical infrastructure. That's just the starting point. The other thing the internet represents is a set of agreements or protocols about how different devices that connect to the internet are going to exchange data now that they can send signals to each other, right? So I can send an electronic signal to some other device, but what am I going to say? And how are we going to structure our conversation? We're going to talk a lot, for the next, few minutes and on Monday about protocols, right? And, that word is really interesting. That word has a history that goes back to the ways that heads of state would interact with each other. There was a protocol when, back in, centuries and centuries ago, when two kings met, there was a protocol for how they would meet in terms of, and this is still true when two heads of state meet. There are protocols for, how many people are there, who shakes hands first, whatever. These are agreements about how to arrange communication and interaction between two different things. And on the internet, we use these protocols to structure communication between different devices that are all connected to the internet. And this is the only way that we can make sense of this huge commons that we've built, right? We've essentially built this huge system in which any two devices can communicate with each other, but we need protocols so that that communication could proceed smoothly and in a way that achieves some desired result. So the internet, again, represents physical infrastructure, but there's also something called, literally, the Internet Protocol, or IP. If you've heard of TCP/IP, if you've heard of IP address, this is what it stands for, the Internet Protocol. And on some level, what defines the internet is as much the Internet Protocol as the hardware that we've set up to enable the Internet Protocol, to enable communication. There's actually a lot of different protocols that we could have built on top of the same hardware. So we could have, if we decided today for some reason we wanted to start over, we could reuse all the same existing wires and switches and stuff like that and just build a different communication protocol on top of that. That would require some changes, but a lot of the physical infrastructure would still be useful. But the protocol we've come up with is something called the Internet Protocol. And this consists of a series of agreements that allow two internet-connected devices to communicate with each other. This protocol addresses a couple of different questions. So one of the things that's notable about the IP protocol, however, is how minimal it is. But it does need to solve at least a couple of problems. So one of the first problems it solves is, what do we call each other? How do we name each other on this huge commons that we've built, where now all these devices can talk to each other? In order to send a message to somebody, I need to, it's like sending a piece of mail. I need to write a to address on that. Otherwise, there's no way that the message is going to get there. So what are we going to call each other? This problem of naming. That's where the term IP address comes from. This is an Internet Protocol address. It's an identity. It's an address on the internet that allows a device to receive data. Okay. IP addresses have gone through a couple of different changes over time. So here's one example IP address. You guys may have seen these before. This is in the format called dotted decimal notation. It consists of a series of numbers between 0 and 255 separated by periods. That's just a way of formatting. Essentially, this is a 32-bit number. Probably the only mistake, and this was acknowledged by the people that invented a lot of this stuff, probably one of the only mistakes that the internet designers made is that the original internet addresses, so this is an Internet Protocol address version 4, the original internet addresses were too small. So if you think about it, 32 bits, how many different addresses can I represent with 32 bits? The total is 4 billion. Now, there's already more people than that on Earth, and many of those people have multiple devices. So it's clear that the IPv4 address space is not large enough to provide every device on Earth, or every device that might exist on Earth someday, with a separate address. And so again, the original internet creators have kind of said, yeah, I wish that we had realized how successful this thing was going to be, because we would have made a slightly different choice here. What we're moving towards as a way of addressing this limitation is something called IPv6. So this is a new version of the Internet Protocol. IPv6 allows for much larger IP addresses. So the addresses go from being 32 bits to being 128 bits. That is much, much larger. IPv6 allows us to assign a separate internet address to every atom in the universe. That is probably enough. And IPv6 also structures those addresses a little bit differently. Some of you may have seen an address like this. Some of you may not. But in the future, more and more devices on the internet are starting to use IPv6 addresses in the IPv6 protocol. And so these addresses are going to become more prevalent. The other thing that IP does, so first thing IP does is it says, okay, here's how we're going to name, here's how we're going to set up our names so that I can identify you when I want to send you a message. The second thing IP does is it provides a minimal structure for the message itself. So IP says, we're going to exchange messages over the internet in this particular way. You're going to package up a chunk of data, and then you're going to give it to the internet. The internet's going to try to make sure it gets to the right place. Inside that message could be all sorts of data of any format that you specify. But we do need to agree a little bit about sort of the envelope. So think about sending a letter, right? What you put inside that envelope is your business. But in order to deliver it, the post office has some rules about how the outside looks and where you put different pieces of data, right? My wife recently was sending some letters to her friends, and one of them got returned to sender, and we looked at it, and she had forgotten to write the address. She basically just wrote the friend's name on it, and I was like, honey, the post office probably doesn't know exactly which friend that you wanted to deliver this to, right? So we come up with an agreement about what the outside of the envelope looks like, but what you put inside the envelope is totally up to you. The post office doesn't care, right? Like you could put anything in there, as long as it's not, white powder or something. So here's the actual format of what's called an IP datagram. This is an IP message. And I'm not, you're not going to be tested on this. We're not going to go over this in detail. I just wanted to show you a couple of things that are in here. The most important bits are this source IP address, which is right here, and then the destination IP address. And again, this is very much like a letter. When you send a letter, you tell the post office where you want it to go. That's the destination address. And you also put a return address on it. That's where it came from, the source address. Then down here at the bottom, it says data. And the idea is that you put a little bit of information at the front of your message that allows the internet to figure out where you want that message to arrive. And then you put a bunch of data at the back of the message, and that data can be anything. And this is actually one of the things that's so beautiful and cool about the Internet Protocol, is that it doesn't have any rules about the data that you put in the message. This is one of the ways that's allowed it to support so much innovation. We're going to talk about that more in the future. Before we wrap up today, I do want to, try to bring a more human take to this, right? in terms of, again, things that have changed the world around us, to me, the internet is up there as probably number one, right? I mean, this is by far, and it's also, I think, one of the most beautiful things that humans have ever created, because it's not like a bomb, right? It's not something that we created that is harmful, right? I mean, drugs and vaccines are up there as well. Obviously, that's something that we're all going to appreciate once this happens over the next couple of years. But in terms of technology, the internet is not only, been wildly successful, right? I mean, nothing has changed the world and continues to change the world the way that the internet did. But it's also fundamentally something that should be, it's not always, again, there's lots of, you can come up with lots of bad ways in which the internet is changing the world, but those are kind of our fault, right? The internet has also opened up a huge amount of positive space in the world for us to do cool little things. The people that created this are largely anonymous, right? I mean, who invented the polio vaccine, right? We still remember some of the names of people that, invented, at least were able to mass produce automobiles, right? I suspect many of you, until today, had not heard the names Vint Cerf and Bob Kahn, but these are some of the small group of people that created this incredible system. And so I think the other thing I've always found inspiring about the internet is just how little credit the people that built this have demanded of us, right? They built this system. It has changed the world around us in ways that none of us could have anticipated. It's the ultimate flowering of our, species' desire to communicate with each other. And yet the people that built it, that created it, that set up some of the first protocols have been content to, in many cases, some of these people are starting to die off right now. They're at that age, right? And, a lot of them never became famous. They never became notorious. I mean, Vint Cerf has become slightly famous, but that's, I think, at least partly because he has this endearing habit of wearing three-piece suits all the time. He now works at Google. But one of my favorite stories about this. So these guys were graduate students when they did a lot of this work. At the time the early internet was being set up, essentially what was happening is these devices that would then constitute part of the internet backbone, an early version of it, this was like in the 1950s, were arriving at various universities. And there were these really excited graduate students that were waiting for them that couldn't wait to tinker with them, right? And to figure out how to get them to work. One of my favorite stories about this period of time is recounted by some of these people is that they said, we always figured that somebody was in charge, that at some point there are some adults in suits were going to show up and they were going to say, okay, you graduate students, you've had your fun, but we know how to do this. And it turned out those adults didn't exist, right? These people, set up and built some of the early protocols that we're still using today without any sort of guidance because no one knew what they were doing, right? They were just these grubby graduate students. They changed the world. All right, so I am done for today. I think what we'll do next time is we'll pick up, talk a little bit about packet switching and how the things move around on the internet. Okay, so a couple of quick announcements. I know I'm over time, but just as a quick note about scheduling, and this is on the schedule, and I'll send out an email about it as well, but the last quiz, our last midterm, is going to be on Monday of the final week, Monday at 10 a.m. So rather than having class on Monday, we're going to take the last midterm exam. Part of the reason for this is that I don't want to end the semester with an exam. Our last meeting is on Wednesday. We have a tradition of what we do on that day in class, which is we go back and we review all of the really incredible work you guys have done throughout the course of the semester, talk a little bit about the future. And so instead, on that last week, we're going to make the schedule change. We'll have the final midterm Monday, May 4th, 10 a.m., no class that day, and then on Wednesday, we'll have one final time to get together and talk about all the amazing stuff you guys did. Final project description is out. Please get started on it. Please also keep in mind that grading on this is extremely generous. Do something and you're likely to get full credit. Do something cool and I will try to bring as much attention to that as possible. I don't have office hours today from 1 to 3 p.m. That's a bug on the slide, but I will look forward to seeing you guys on Monday at the same time. I hope everybody is taking good care of each other and the people around you. Stay safe, stay well, enjoy your weekend. I will see you again on Monday.